What problem does the proposed method aim to solve compared to existing transformer architectures?
The proposed method aims to solve the problem of positional encoding, PE, lacking faithfulness in existing transformer architectures. The existing PE methods, such as the original sinusoidal PE, have limitations in faithfully representing the position function of items in a sequence due to their strong low-pass property and lack of sensitivity to short-range dependencies. The proposed method, called DFT encoding, leverages the discrete Fourier transform DFT to create a smooth surrogate for the one-hot position function, ensuring faithfulness by being injective one-to-one to the position function. By using DFT representation as a basis for positional encoding, the DFT encoding method addresses the issue of the original PE, not accurately reflecting the position of items in a sequence. The DFT encoding method provides a principled and optimal way of deriving positional encoding that meets the faithfulness property, improving the classification task performance in transformer architectures.
How does the DFT encoding method work in positional encoding step of the transformer algorithm? Explain step by step.
The DFT encoding method works in the positional encoding step of the transformer algorithm by leveraging the discrete Fourier transform, DFT, to create a faithful positional encoding. Here's a step-by-step explanation. 1. Mapping to smooth function. The positional encoding, PE, is viewed as a mapping from a localized position function, one hot vector, to a smoother differentiable function to ensure faithfulness. 2. DFT encoding. The DFT encoding method computes the DFT coefficients of the one hot function representing the position of the item in the input sequence. 3. Vector representation. The DFT coefficients are computed against the real Fourier bases to obtain a vector representation of the one-hot function, which is the DFT encoding. 4. Faithfulness. The DFT encoding is proven to be faithful by showing that it can fully reconstruct the original position function using the inverse DFT transformation. 5. Inverse transformation. The inverse DFT of the DFT encoding ensures that the reconstructed function is the original position function, demonstrating faithfulness. 6. Distribution in Fourier domain. The distribution of the DFT encoding in the Fourier domain is flat, without bias on the choice of Fourier components, unlike the original PE. 7. Reconstruction experiment. The reconstruction experiment confirms that the DFT PE perfectly reconstructs the location functions, indicating its faithfulness to the position function. In summary, the DFT encoding method in the positional encoding step of the transformer algorithm utilizes the DFT to create a smooth and faithful representation of the position function, ensuring that the positional encoding captures the order and interdependency of items in the input sequence accurately.
What are the theoretical benefits of using the DFT encoding method for positional encoding in the transformer algorithm?
The theoretical benefits of using the DFT encoding method for positional encoding in the transformer algorithm lie in its faithfulness property. The DFT encoding ensures faithfulness by providing an injective mapping from the position function, one hot vector, to a smooth surrogate function represented by DFT coefficients. This faithfulness property guarantees that the positional encoding accurately reflects the position of items in the input sequence, capturing both short-range and long-range dependencies effectively. The DFT encoding method leverages the properties of the discrete Fourier transform, which is invertible, allowing for the full recovery of the original position function from the DFT coefficients. This invertibility ensures that the positional encoding retains all the information of the position function, making it a reliable and accurate representation of item positions in the sequence. Additionally, the DFT encoding method does not introduce bias in the choice of Fourier components, leading to a flat distribution in the Fourier domain, unlike the original PE method, which had a strong low-pass property. Overall, The DFT encoding method in positional encoding enhances the transformer algorithm's performance by providing a principled and faithful way of representing item positions in sequential data, thereby improving classification task performance and capturing dependencies more effectively.
How was the faithfulness of positional encoding addressed in the proposed method, and why is it important?
The faithfulness of positional encoding was addressed in the proposed method by introducing a new notion of faithfulness and deriving a new positional encoding (PE) method called the DFT encoding. The goal was to create a PE that is faithful, meaning it holds the full information of the position function and can be considered one-to-one. The DFT encoding leverages the theory of discrete Fourier transform to ensure faithfulness by mapping a localized position function, one hot vector, to a smoother, differentiable function. The faithfulness property is crucial because it ensures that the positional encoding accurately reflects the position of items in the input sequence, capturing both short-range and long-range dependencies effectively. By being faithful, the PE can provide a richer representation that not only conveys information about individual items, but also their relationships with other items in the sequence. This is essential for tasks like time series classification, where understanding dependencies between elements is vital for accurate predictions. The faithfulness of the positional encoding is key to improving the performance of the transformer algorithm in capturing the order and interdependency of items in sequential data effectively.
What were the specific results achieved with the DFT encoding method in the time series classification task?
The specific results achieved with the DFT encoding method in the time series classification task were successful reconstruction of the location functions, demonstrating faithfulness of the positional encoding. The DFT encoding method showed a flat distribution in the Fourier domain without bias towards specific Fourier components, unlike the original positional encoding. The reconstruction experiment using the DFT encoding method resulted in perfectly reconstructed location functions, indicating the ability of the DFT encoding to faithfully represent the position function. This successful reconstruction confirmed the faithfulness property of the DFT encoding method, showcasing its effectiveness in capturing positional information in the time series data.
What are the limitations or drawbacks of the proposed DFT positional encoding method in the transformer algorithm?
The limitations or drawbacks of the proposed DFT positional encoding method in the transformer algorithm are not explicitly discussed in the provided text. However, one potential limitation could be the computational complexity introduced by the DFT encoding method. Since the DFT involves transforming a function defined on a one-dimensional lattice with d lattice points into a set of coefficients, this process may require additional computational resources compared to simpler positional encoding methods. Another limitation could be the requirement for a specific structure in the positional encoding vectors, as the DFT encoding method relies on the assumption of sinusoidal bases. This may limit the flexibility of the positional encoding approach and its applicability to diverse types of sequential data. Additionally, the DFT encoding method may introduce challenges in interpretability, as the transformation into Fourier components may make it harder to intuitively understand the positional information encoded in the representation vectors.